Previously, we took the law of exponential change, where dy over dt equals to ky, so y is directly proportional to the slope. Y equals to y0 times e to the power of kt, giving this exponential graph, where nothing is limiting the growth. Wait, but what if y is not directly proportional to the slope, and there is a limiting factor, such as food or space? Well, then that's what we call logistic growth. For logistic growth, dy over dt equals to ky times c minus y. So let's try to graph this. When y equals to 0, let's replace y with 0. Dy over dt will be 0. So at that point, y is unchanged. Let's replace y with c. Replace y with c. Dy over dt will be 0, c. So y at c is 0, unchanged. You may wonder, what about between 0 and c? Well, that's where it gets a bit complicated. So, when y is between 0 and c over 2, slope increases as y increases, giving us this exponential shape before c over 2. After c over 2, however, slope decreases as y increases, giving us this shape. And overall, this is how the graph will look like. So at c over 2, we have an inflection point where slope changes direction. Unlike exponential growth, logistic growth has a limit called the carrying capacity. So now let's find y as a function of time. So first, separate the variables, integrate both sides, then using partial fractions that we took last lesson, find the integral. So after several simplifications, we get this boring integration, right? Let's take a question. The question states that the growth of a bear population is modeled by this equation, where t is in years. A. What is the carrying capacity? We have our original equation where c is the carrying capacity, so it's 100. So the population will keep increasing until it reaches the carrying capacity 100 bears. B. What is the bear population when it's increasing the fastest? So the derivative of the derivative equals to 0, so the inflection point is at c over 2 as we stated before, which is half of the carrying capacity, which is 50 bears. C. What is the rate of change of the population when it's increasing the fastest? We have the equation of the rate of change, replace P by the number we got in part B, and we get 20 bears per year. Through integration and partial fractions, we turn this to this, giving us this graph, which is logistic growth.